Welcome to the first lecture in Module 3. We'll be covering sensory perceptual development, which is covered in Chapter 10 of our textbook. We'll be going over the development and aging of vision, audition, kinesthetic perception or proprioception, and intermodal perception. To start, let's talk about what perception is and why it's important. Since we've established that human movement emerges as a result of the interaction of the individual with the environment, the ability to gather information about the environment is essential in creating that interaction. In order to gather the information, we must perceive the information through our senses. We need to establish some definitions that differentiate sensation from perception. Sensation is sensory information that causes neural activity triggered by a stimulus that activated a sensory response and is a passive process. Perception, on the other hand, is the process of selecting, processing, organizing, and integrating information received from the sensory receptors and is a more active process. So sensation is the information and it's passive, and perception is selecting and processing this information, which is active. Let's first talk about vision and how it changes throughout development. The infant at birth has very poor vision and cannot really recognize anyone based on static vision. However, it can perceive movement, and perception of objects around improves if either the perceiver or the object moves. This chart shows us the development of vision, and we can see that children do not develop 20/20 vision until they're into childhood. The next few slides show us how the static image changes throughout the first few months and how it compares to adult vision. So we can see here that at the first month, this picture is very blurry. 2 months gets a little bit clearer, but it's still pretty blurry. 3, you get a little bit more of an idea of what we're trying to look at. And finally, as an adult, we see the person's face. The infant also does not have too much control over their eye movements, as the eyes often appear to move independently, which is a little bit scary, honestly, if you see an infant moving one eye at a time. The infant has difficulty moving eyes together and has difficulty making smooth pursuit movements, so they only end up making saccades, so they jump from one place to another. In order to test the importance of vision in neural development, researchers in the 60s designed a visual deprivation experiment where they determined the visual experiences directly affect the wiring of the brain. They deprived kittens and monkeys of visual experiences by sewing their eyes shut shortly after birth. This is really terrible, and it honestly makes me very unhappy that this form of animal cruelty was allowed back then. So, even though we're talking about this, I just want to throw a little caveat in there that this makes me really sad. In spite of how terrible this was to the animals, their findings were interesting because they found that the neural wiring was more disturbed when one eye was sewn shut compared to when both eyes were sewn shut. When one eye was sewn shut, there was a lot of space lost in the visual cortex. When both eyes were sewn shut, the visual system is reduced, but the cortical development was relatively symmetrical. This shows us that there is a competitive interaction between the left and right eye input that underlies the process of selective brain wiring. When taking a look at the brain tissue of the monkeys who experienced the visual deprivation, we can see that when one eye is sewn shut, the inputs from the open eye win all the activity contests, and the disadvantaged eye has little access to the circuitry. They found that the closed eye remains functionally blind even after it's open. They also found that there is a critical period in which the visual input needs to be present. They found that the first 3 to 4 months are the critical period, and sewing the eyes shut after that period of time was less devastating. Early experiences really shape visual development. Canadian Native people often lived in teepee-shaped dwellings, which develops a better acuity for oblique angles. And many children are cross-eyed early in life, and visual experiences often self-correct this problem. The development of color vision in children is very difficult to assess, but most researchers believe that infants are able to perceive colors at birth. Some of the limitations of being able to really tell before 2 or 3 months is the poor contrast sensitivity that the infants have at this age. The peripheral vision of children is not as good as adults, as the full range of infant vision is about 120 degrees, while an adult range is about 180 degrees. This means that objects need to be placed directly in front of the infant in order to capture its attention. Depth perception is also something that's developed. There is retinal disparity that exists as each eye sees a different visual field from a slightly different angle. The cortex needs to compare two slightly different pictures in order to determine the spatial arrangements of the objects of interest. This also occurs when the person is in motion. Nearer objects overlap more distant objects as the head moves. This is the concept of optic flow, where the optical array is constantly being transformed as we move. So how do we study depth perception? Their observations, questionnaires, and interviews are generally the ways that we conduct research in kinesiology. But to study depth perception, experiments are really the best way. Two experimental designs used to study depth perception are the visual cliff and the preferential looking experiments. We're going to watch this video about the visual cliff paradigm and how the development of locomotion affects depth perception.
Post Lab at Berkeley has devised a series of experiments. Kaylin is put on the visual cliff. One half of this plexiglass surface is solid looking, but the other half is transparent and seems to drop off. Kaylin is a very new crawler and hasn't learned fear of heights yet. Although she sees depth, she happily crosses the abyss, not understanding what depth means. Reese has been crawling for a few weeks more than Kaylin.
Look at the butterfly. You want to come get the butterfly?
She reacts very differently on the cliff.
Come on. You want to come get it?
Even though her mother calls her, she refuses to cross.
Come on. Come on over.
She shows the classic fear of heights.
Come get your duck. Come on. Come on. Come on.
The only difference between Reese and Kaylin is the amount of experience they've each had crawling.
Come on. You can do it.
What is it about crawling that teaches the baby human fear of heights?
So we can see from that video that the experienced crawler had developed the fear of heights. And it really shows how perception affects our actions in our environment. We'll pause the video here and we'll continue talking about the next experimental paradigm in the next lecture.